let's say we have a pulley, and we have a mass on a surface and a mass hanging off an edge. We'll call this mass 2, we'll call this one mass 1, and this one is the pulley. Now, we know the mass of the pulley. We know the mass of the first block. We know the mass of the second block. We know the radius of the pulley. We know the pulley is a solid disk. And we know there is 0 friction between the surface and block 2. That's right, we're going to have no friction this time. You're welcome. And we are going to try to figure out the acceleration of the 2 blocks. Now, there is a way we could do this without stuff from chapter 11, but I'm going to show you how to do it using stuff from chapter 11, and we'll talk about how we could have done it without stuff from chapter 11. We're starting here with something we could use chapter 11 to solve, or we could use stuff before chapter 11 to solve, because that helps us to understand stuff before we get to stuff where we couldn't have used stuff. But anyway, here we go. Let's start with a free body diagram. I'm actually going to draw the free body diagram over here, not to confuse that picture. If we could have, please, the free body diagram. Nitish, free body diagram, block 2.
Tension going left. Force of gravity down. And force normal up.
Keep going.
Okay.
Block 1.
Oh, force of gravity down.
Uh-oh.
And then tension.
Oh, I'm sorry. We had 2 things labeled force of gravity.
Oh, force of gravity 1 and then force of gravity 2.
Can't have 2 things labeled the same thing. Keep going.
Tension 1 up. And then the other one would be tension 2.
Pulley.
And there's the force of gravity of the pulley. It's down. And the force normal holding it up.
Uh-oh.
Force normal pulley. Force normal 2. Tension going down. Tension 1. Tension 2 going right.
There is a complete free body diagram. Great. The moment of inertia of the pulley is going to be equal to what? We have 2 equations for moment of inertia. The angular momentum of the pulley is going to be equal to what, Garrett? We have 2 different equations for the angular momentum. Which equation are we going to use?
The moment of inertia times angular velocity.
Why?
It's a rigid object.
This is a rigid object with shape as opposed to a point particle. We have the moment of inertia of a solid disk. What is the equation for the moment of inertia of a solid disk? You have derived it several times. It was on your test. Class. 1/2 mass of a pulley times the radius squared. So we have 1/2 mass of the pulley times the radius squared times the angular velocity. We already figured out that the angular velocity equals the tangential velocity divided by the radius. That seems like that's something useful to plug in here. So we have 1/2 mass of the pulley times the radius squared times the tangential velocity divided by the radius. One of the radii cancel out, and we get 1/2 mass of the pulley times the radius times the tangential velocity. That's the angular momentum of the pulley. Now, we can also figure out the angular momentum of our 2 blocks. Now, these are point particles, but they still have angular momentum about this point right here. What equation are we going to use to figure out the angular momentum of block 2? Sierra?
Do we use the parallel axis?
The parallel axis theorem would be to figure out, for example, the angular momentum, the moment of inertia of this pulley about some other axis other than its center of mass, which is not what we're doing here. We need to figure out the angular momentum of this block, which is a point particle. We're going to use what equation, Sylvan?
RMV something.
We're going to use R cross P or RMV sine theta. So this is going to be the lever arm of 2 times the momentum of 2. So this is lever arm of 2 times the mass of 2 times the velocity of 2. Now, I'm going to draw a picture so we understand what's going on here. We have the pulley. The pulley is here. It has a certain radius. And then we have the string. The string is attached to block 2 right here. Block 2, which is right here. We have our surface, looks like this. Now, this big R is the radius of the pulley. This R2 that we have right here is actually this right here, because this is the lever arm. The distance from the axis of rotation, this is, we're taking the angular momentum about this point and the point where the velocity of the object is. Now, this is our theta. If you look, we have this velocity here for the angular momentum of the pulley. But we have a problem as time goes by here. Does R2 change for mass 2, class?
Yep.
Yes. Does theta change as mass 2 moves?
Yes.
Yes. So we have a situation, we have 2 different variables which are changing as this mass gets closer to the pulley. Now, there is a solution to this, and it is one that's going to come up many times, and it involves sine of theta equals opposite over hypotenuse. Opposite theta is big R, the radius of the pulley. The hypotenuse is R2, the distance from the block to the point at which we're summing the angular momentums about, which we'll be doing shortly. And so what we get is that R is equal to R2 times the sine of theta. Now, I understand that R2 changes as a function of position, and so does theta. It changes as a function of position. But does the quantity R2 times sine theta change as a function of position? No. So we can replace R2 sine theta with the radius of the pulley. So the moment of inertia of block 2 about the center of mass of the pulley is equal to big R, the radius of the pulley, multiplied by mass 2 times the velocity of object 2. So it's going to come up a lot. So it's something you need to pay attention to, something you are going to repeat. I know you don't know where we're headed yet. Don't worry, we'll get there in a minute. We figured out the angular momentum of the pulley. We figured out the angular momentum of block 2. We're going to figure out the angular momentum of block 1. We are, again, going to use R1 cross P1 or RMV sine theta with a bunch of 1s. Notice that the same thing happens here, right? I'm not going to draw the picture. It's going to be identical over here where we have the radius and we have theta and R1. So what can we replace for the angular momentum of block 1 here? Look. I need the whole equation.
Oh, sorry. RM1, P1.
Because we're going to end up with the same thing where big R is also equal to R1 times sine of theta 1. Okay. So we have figured out the angular momentum of everything. So we can figure out the angular momentum total about this point, the center of mass of the pulley. is equal to the angular momentum of block 1, R m1 v1, plus the angular momentum of block 2, R m2 v2, plus the angular momentum of the pulley, 1/2 the mass of the pulley times R times Vt. So you can see we have R times V in all of these, and the velocity of 1, the velocity of 2, and the tangential velocity of the outer radius of the wheel are all going to be the same thing. So we actually have R times V times the quantity m1 plus m2 plus the mass of the pulley. This is the angular momentum of the total system about this point, the axis of rotation of the pulley.
Mr. Palmer?
Yes?
Should it be 1/2?
Thank you. Thank you. Yes. Because I dropped the 1/2. Okay. Now what we're going to do is we're going to sum the torques on the whole thing about the axis of rotation of the pulley. And this is the whole thing. Please list all the torques. Match. Torque due to what? Go back to the free body diagram.
Torque due to tension 2. Torque due to tension 1. Do I have to say the force normal one, even though they don't really exist?
You got to list everything. We'll talk about, bless you, why they might or might not cancel.
Torque due to force normal of pulley. Torque due to force of gravity of the pulley. Is there another torque for the blocks or not?
We're doing the whole thing about this point right here.
So
Keep going.
Like so all the forces. I mean,
Every force.
So they don't really have torque.
Yes, they do. This applies a torque about this point right here.
Okay. All right. So torque due to force normal 2. Torque due to force of gravity 2. Torque due to force of gravity 1. They already said the tension, so.
But there are 2 of them.
Oh, why don't they have different subscripts then?
We'll get there.
Torque due to tension 2. Torque due to tension 1.
Right?
Yeah.
Because if we're going to sum the whole thing, we've got to list every force. Okay.
Was that? Is that not all of them?
I don't know.
That's
Let's
all.
see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Are there 9 there?
Yeah.
Good. That's all.
So it equals the moment of inertia.
Right. I'll add that in a little bit because I ran out of space. We'll get there in a minute. So now, torque due to tension 2. We need to define a positive direction. Remember, you've always got to define a positive direction. So one of these torques due to tension 2 is going to be positive. One is going to be negative. So they cancel one another out. We're going to have torque due to tension 1. Again, one is going to be positive, one is going to be negative. They're going to cancel one another out. What about the torque due to the force normal of the pulley and the torque due to the force of gravity of the pulley? Rohan?
Are those
Because they actually don't cancel. These cancel, but these don't cancel one another. So did you have them out?
they have no lever arm?
They have no lever arm. So these are actually both equal to 0 because their lever arms are equal to 0. Torque due to force normal 2. Torque due to force of gravity 2. Neither of those are 0. But do you notice, if we were to sum the forces on this block in the y direction, what do you know about force normal 2 versus force of gravity 2? They're equal but opposite, and they act at the exact same location. So these two actually cancel one another out because they are equal but opposite. Which means we're left with the torque due to force of gravity 1. Is it positive or negative, Lad?
Which one?
The torque due to force of gravity 1.
It's positive because we're in the center.
Because if you look, we set the positive direction in that direction. So in the end, the net torque about the axis of rotation of the pulley of the whole thing ends up being equal to the torque due to the force of gravity on what? Everything else cancels out. That is equal to, now the only way we could sum the torques on the whole thing is if we use the derivative of the angular momentum of the whole thing with respect to time. Okay, torque due to force of gravity 1. That's going to be force of gravity 1. Let's do it this way. It's going to be the lever arm for 1 times the force of gravity 1 times the sine of theta for 1. That's going to be equal to the derivative of, well, we have the total angular momentum. It is R times V times the quantity M1 plus M2 plus the mass of the pulley divided by 2. Looking from left to right, what do you know about the lever arm for force of gravity 1? Nick?
Say that the lever arm times the sine of theta 1 is big R.
Actually, it's easier than that. The force of gravity 1 essentially acts from right here, right?
So it's just 90.
Well, so the angle is 90, I agree with that. And what's R1?
Big R.
Big R. And force of gravity 1? M1 times G. On the right-hand side, let's make it a little bit easier. Let's take out the things that don't change as a function of time on the underneath this derivative here. Meg, what doesn't change? Or actually, either does or doesn't change.
The mass.
Masses are constant.
Masses are constant. And the big R is constant.
Then the radius is constant. So we have the radius multiplied by M1 plus M2 plus the mass of the pulley divided by 2. All of that multiplied by the derivative of the velocity as a function of time. Class, what's the derivative of velocity as a function of time? Acceleration. So we get sine of 90 is just 1. We get, oh, I missed it. Hold up, I gotta
Radius.
We get a different sound for different variables.
I don't know. That would be a good idea. No, I haven't thought of that. That's a good one. We'll just do this one right now. That's what I got. Everyone brought R to the party. We could be equitable. We could take R from everyone. We end up with, because this is equal to acceleration times M1 plus M2 plus the mass of the pulley divided by 2, we get that the acceleration equals mass 1 times the acceleration due to gravity divided by the total mass of the system.
Mind blowing.
That is the answer. Okay. Now, as I said, that is one, yes, that's one way to solve it, Tim.
How do you know that torque due to force of gravity 1 is equal to derivative of angular?
Going back to the equation, we know that the sum of the forces equals the derivative of the linear momentum as a function of time. And we also know that the sum of the torques external is equal to the derivative of the angular momentum as a function of time. It just goes back to the rotational version of Newton's second law using angular momentum. So that's one way to solve it. I'm not going to go through, well, I guess I'll start one of the other ways to solve it. There are actually two other ways that I can think of to solve this. One of them would be to sum the torques and sum the forces. Now, we could sum the forces on block 2 in the x direction. It would be negative tension 2, actually it would be positive because we defined that as a positive direction. Positive tension 2 equals mass 2 times the acceleration. We could sum the forces on 1 in our tangential direction, which would be equal to force of gravity 1 minus tension 1 is equal to mass 1 multiplied by the acceleration. I guess I'll do this. In the parallel direction, I think is the way to describe that. And we could also sum the torques. Now, this would only be on the mass of the pulley about the axis of rotation of the pulley. So this would be different in this particular case, because what we'd have is we'd have the four forces, or four torques acting on the pulley. The torque due to the force normal of the pulley, the torque due to the force of gravity of the pulley, the torque due to tension 2, and the torque due to tension 1. These would both be 0. Torque due to tension 2 would be negative. Torque due to tension 1 would be positive. And notice, this would be equal to the derivative of the angular momentum of only the pulley with respect to time. So notice that this is a different approach. Rather than doing it on the whole thing, we could do it piecemeal. And if you look, you're going to end up having 3 equations and 3 unknowns and having to solve by combining all of them to get to here. So in the end, this only has 1 equation, which in the end is easier to solve than this. What's another way we could do it? We talked about we have some of the torques up on the whole thing about the axial rotation of the pulley. We also have some of the forces and some of the torque about the pulley. There's one other way to do it. Okay. Is there friction in the problem? So we could have used conservation of energy, but you would need to remember that the pulley has rotational kinetic energy.